distinguished scholars here, thank you so much. I'm really overwhelmed. And then from this time on, for about 40 minutes, I give a talk in front of you, and about particularly Japan's way for technological developments in building, design, and construction. Mr. Jaime kindly introduce my technical works for the past 30 years. But many of them, small pieces of research endeavors, therefore probably not so fun to many of you. Now, instead, I bring this material. Why Japan is different from the rest of the world? Okay, my story begins like this. By the way, what is Masayoshi Nakashima? I skipped it because lengthy introduction completed already. Now, two topics I have brought today. One is Japanese culture to building construction. The other one is Japanese attitude to technology development. Now, I first I start from the first topic. Few phrases now I'm mentioning now. Japan is green, featured with wood culture, different from yours. Japan loves detail, which really characterizes Japanese architecture. Third, Japan loves handicraft and manufacturing. Fourth, Japan exercises positive collaboration between design and construction and manufacturing. Those are the four subtopics. And then the rest of the time, I just supplement. Japan is green. Traditionally, they would use 9 elements rather than plain elements. Then popularity of steel is as an extension of wood culture. In fact, in Japan, steel is very popular. Why? Let's go. Now, this is a country of Japan. We are blessed with mountains and wood. And when we go to countryside, we can still find old wood houses here and there, like those. Then, resemblance between wood and steel. One is steel, the other is wood. Nearly the same. Blaming. How about connections, how we join? See? Again, one is wood, the other steel. Very much the same. So this way, then Japan traditionally use the wood, therefore Daishi Temple, world largest wood building. And this is Nagoya Dome made of steels, but from the distance, they look similar. 5-story pagoda, tallest wood tower, world tallest wood tower. And then Eiffel Tower in the middle, Tokyo Tower on the right, again from the distance, nearly the same. So Japan is destined to use and love steel by culture. Then, so in fact, to my understanding, two basic materials for building construction. One is wood, the other is stone. And then I think my understanding is Mexico has a stone culture. Then stone culture moved to reinforced concrete. Wood culture moves to steel. Two different worlds. I come from the other side of the world. Now, steel is characterized by fast construction, you understand? Quality control, easy quality control, and versatile applications for small, large, tall buildings. And this picture shows the year of construction versus the percentage of the respective type of materials for building construction. Steel, wood, reinforced concrete, and then composite. So steel and wood side by side. We are wood culture. Now, second topic. Japan loves detailing, which characterizes Japanese architecture. What is that? Complicated roof details, exquisitely crafted eaves, complex connections using interlocking others, and then like this. we inherited many of those masterpieces built in the past 15 centuries. How it goes, no names, no nothing. Look at that, collection made of exquisite interlocking. There are many pieces and then with decorations. So this really characterize Japanese wood structures. And this also goes to the contemporary design construction work. This is by the City Hall of Izumo City in Shimane Prefecture. Okay. Now, in fact, there is Izumo Shrine, originated in 12th century, a current main shrine built in 1744. This shrine is famous for god of marriage. So, young people, if you want to get a good partner, go there and there's a good chance. So, famous shrine. Please remember this, right? See, the shape. Original structure, now Izumo City Hall, somewhat similar. Then this facade is now, this one is like this, but this is a shear wall. And this is a vertical lines like long timber columns, but this is CFT. So this way, again, we like to, right, make the resemblance between the past and the present. Next one is Japan loves handicraft and manufacturing. What is this? See, like this, respect to craftsmanship. So there are too many to remember. Armor, umbrella, pottery, handy. And then Japanese is basically clever with hands and fingers. So bamboo work, knitting, weaving, swordsmiths, others. So we are good at hands, relatively. Then, say, because of this, Japan loves innovation via manufacturing. This again is the characteristic that features Japan. Now, within the scope of steel, see, there are many developments done in Japan. High performance steel, ultra high strength steel, fire resistant steel, high toughness steel, ultra high strength, many, right? And also, next to the material, we have elements and devices, buckling restraint braces, some of them you may have heard, or concrete films, steel tubes, etc. They are basically not necessarily originated in Japan, but very much developed in Japan. See, high performance steel, fire resisting steel. Fire resisting steel means right, there's something special such that the strength will not go down with high temperature. Therefore, no fireproof needed, like that. Or say high strength is on one side, low strength is on the other side. Low strength steel intentionally low, then used as an energy dissipator. Or these days, in the name of CO2 reduction and environmentally friendly, we develop different types of steel as well. And then buckling restraint braces. Braces normally good in tension but bad in compression because of buckling. But then we wrap like this, the brace, and then to avoid any buckling. So this has been quite popular lately in many countries. Or CFT. It's simple. Here is a box, and we put concrete in it, and that's it. Nothing else. No reinforcement. But still, this exhibits good ductile behavior. And all of those, we like manufacturing. And then manufacture-oriented research developments are some of the keys that, again, characterize Japan. Now, the last topic about my first subject. Japan exercises collaboration between design and construction. What is this? One is equal partnership between design and construction. The other is quality assurance by disciplined construction. Japan, we have so-called Big Five, general contractors. Obayashi, Kajima, Shimizu, Taisei, Takenaka, those big firms. What characterizes them is they have active in-house research and development institutions. All of those five, they have in-house say, research institutions themselves. And then what they do is here. They do design, and they do research and development. Not only those, they do construction. That's the biggest portion. And then that's the Japanese way, is positive interaction among those three sectors for construction, ultimate construction of buildings, and also traditionally, of course, everything is relative, but please look at the culture of respect to manufacturing. Because I see earlier things, slides I show you, craftsmanship, and then, so those all fabrication and manufacturing. So then we have a spirit and culture of this, and make those three components all together to come up with the ultimate quality control. And this may partially because of this special education system in Japan. I am a structural engineer myself, but I did not graduate from Department of Civil Engineering. I graduated from Department of Architecture. Only in Japan these days, Department of Architecture and Building Engineering, as a the department teaches environmental aspect, structural aspect, design, architecture, everything. So, although time is short, but nonetheless, I have to say that at the age of 18, when I entered the university, this department, I wanted to be an architect. But after 3 months, see, I was smart enough to understand I'm not talented. But I didn't have to leave the department. I could stay. And I took a lot of, say, design-oriented courses myself, particularly for the first 2, 3, 4 years. And then many of my friends now are architects. So something is probably embedded into my body, right? Thanks to this department. And this may be a reason why Japanese way works. Now, see, design is important, R&D is important, but naturally most important is construction. How to, right? Discipline the construction. Example 1, morning assembly, everyone has come. Gymnastic exercise, 1-1-1 in the middle. Instruction session for anything right new, or schedule checking all together. Okay, when the time comes in, comes out, they have to clean up all the hangers, and then keeping things tidy, in order, sweeping, solvents all the time. Be safe. So, design. Essentially, design is meant to have respect to, say, fundamentals. But on the other side, construction, they put various details, because this is a key for the ultimate and quality control. I think this is the end of my the first subject. So this, of course, it's a big propaganda, but nonetheless, I really wanted to show what spirit we want to maintain. Now, on December 8, 1987, I had an honor to introduce myself to Professor Rosenbluth. After nearly 30 years, I'm here. I'm overwhelmed. This is me. Let's go to the second subject. A little more technical, but this means say less interesting. But nonetheless, Japan's attitude to technology development. What is this? We have a tendency of positivism or criticism, whatever. So, and we tend to put emphasis on verification in reference to actual behavior or performance. So, the translation is, right? Fundamentals, the theories, and that's good, but we don't trust 100%. We really want to see the reality. And then for the first time, we understand, let's go. Now, 1995, we had the COVID. And then some of the pictures you may have seen, collapses after collapses. And then here we found a clear contrast between in damage between the two buildings, for example. So those two, downtown open. The same side, the shaping is the same. But one, the third story is gone, but the other stood firm. What is the difference between those two? Year of construction. One is pretty old, the other was new. And then new one really good, old one not bad. So then what we have learned out of 20 years of COVID. First, earthquake engineering has a long history of learning from actual earthquakes and earthquake damages. That is, we first understand the problems by seeing the damage, problem. Then we develop engineering to patch them. Now, as far as Japan is concerned, 1964, so we had a near earthquake, and we suffered from serious liquefaction, so building completely top. And then anti-liquefaction research and also practice began after 1964. 1968, we had Tokachi earthquake, then shear failures after shear failures, columns like that. Then reinforced concrete shear failure, how to avoid, became the important issue, eventually reflected into our seismic codes. Now, 1995. What was the biggest lesson? Seismic retrofit. They look the same, but some very strong, some very weak. And a lot to do with the age, but also with the way of construction. Then those not sufficient in the performance with respect to the current standard, they have to move up. This is called seismic retrofit. This, of course, has been said for many years, but 1996, we really confirmed the importance of that. Then, after 1995, the government of Japan put a lot of money onto this special facility called e-defense. What is this? It is a jumbo shaking table of 20 meter by 15 meter in plan activated in 3D. And then this is basically a big table, put the real structure on it, shake it to see if I have. Why we developed we invested to such a huge facilities? Because of this big problem, how to solve. We have many solutions, but please remember our tendency, theories not sufficient. We want to check before the actual application, if it works or not. How to verify that? We need this. That's the reason why, that was the reason behind the whole concept. So then, as many of you know, small scales, nice, but sometimes many of the important behavior of disappear in the course of reduction of the size and scales. So particularly before the application, if our technologies are really fine or not, we want to check this as large as possible, hopefully with that full scale. That is again the concept behind it. Now this is the scheme of shaking table, 20 by 15 meter and 7 meter high. A total mass is several hundred metric ton. It's a big chunk of steel, and then many actuators in both directions to give horizontal motions and also vertical motions as well. And then since 2005, by the way, the e-defense